also just really briefly want to talk about qualitative concentration descriptions. Basically, we have dilute versus concentrated. Something that is dilute contains very small amounts of solute compared to the overall solution. So remember the solute, if you go back to our solubility rules, is whatever is being dissolved in the solution. So if we have a really tiny amount of salt dissolved in something, our water is not very salty, that's considered dilute. Versus concentrated, which contains large amounts of solute in a solution. So our salt water, like in the ocean, is going to have a lot of salt dissolved in it, and that is much more concentrated. So those are basically our two descriptors. We're going to use them a little bit in class, but beyond that, you just kind of need to be familiar with the language. You do, though, need to be very familiar with, we have 4 new-ish formulas, I guess I could say, that you are going to be looking at today. These we're going to be doing practice with in class and using a lot, and they will be on your final. So just like I said earlier, a reminder, our solution includes our solute and our solvent. Our solute is our thing that is dissolved in the solvent, which often is water. So our very first problem our very first quantitative concentration problem that we are going to be looking at is percent by mass. And this is the same when we were doing percent composition earlier this year. And it is basically part over whole times 100. So percent by mass of a solution is going to be the mass of the solute divided by the mass of the solution, which remember is the solute plus the solvent times 100. So our example is, what is the percent by mass of a sodium chloride solution containing 17.5 grams of sodium chloride per 500.0 grams of water? So our percent mass is just the mass of our solute, which is 17.5 grams, divided by the mass of the solution, which is the solvent plus the solute. So we have 17.5 grams plus 500.0 grams. And we multiply that whole thing by 100 to get 3.38%. This 3.38% is telling us that 3.38% of our total solution is sodium chloride. That one's pretty easy. Our second example over here is what we call molarity. And molarity is equal to the moles of our solute, again, divided by our liters of solution. So we refer to it as moles of solute per liter of solution. Again, most likely and often for us, our solution is going to be made up of water and our solute together. So in order to calculate this, again, it's just some division. So the big thing that we normally have to do with this is converting something in grams to moles. So you see I already did this right here. But this question is asking, what is the molarity of a saline solution containing 0.900 grams of sodium chloride for every 100 milliliters of solution? A saline solution just means salt water. So first we're going to convert our sodium chloride from grams to moles using our molar mass. So 0.9 grams of sodium chloride is actually equal to 0.0154 moles of sodium chloride. And then to actually calculate the molarity, we are going to put the moles of solute, which is 0.0154 moles, divided by our liters of solution. But our liters are actually, our solution was given to us in milliliters. So we're going to have to change that into liters, which is 0.100 liters of our solution. And that is going to be equal to 0.154 big M, which is moles basically per liter. This large M is what we refer to that as molar. Okay, and it is equal to moles per liter. Okay, so molar is moles per liter of solution. Our third example and calculation has to do with dilutions, okay? And dilutions are basically making a solution less concentrated. So, come on this side here. Thank you. So our dilutions is when we are just making a solution less concentrated. And we do this in chemistry class often. We do this for you before we do labs. It's a useful thing to know how to do. And again, it's a formula that is similar to other formulas that we have looked at, but it is the molarity times the volume, initial molarity times initial volume, is equal to final molarity times final volume. So we are going to look at what the units look like and how we would actually solve and what a problem would look like looking at dilutions. So the question is, what volume in liters of a stock solution of 2.00 molar magnesium sulfate would you need to prepare 500 liters of 0.4 molar magnesium sulfate solution? So the thing is, that seems like a lot of words, but again, if we just make our variables list, you're going to be able to identify our initial and our final values, and then you just do a little multiplication and division, and we should be able to solve. So our 2.000 molar magnesium sulfate is actually our stock solution. So that is what we start out with, our initial, and that is always your more concentrated solution. And that would be, and then our 500 liters is what we are actually trying to make. So that is our V2, our final volume. And then we are trying to make that 500 liter solution 0.4 molar. Remember, this means that we are moles of solute per liter of solution. So this means this is our final concentrate. This is our final molarity. Okay, so we are trying to solve for how much what is our initial volume that we need to make this solution. So first I want to isolate the variable. So we're going to say V1 is equal to M2 V2 divided by M1. Okay, and then we are going to say V1 is equal to 0.400 molar times 500 liters divided by 2.00 molar. And then you can see that our molarity cancels out and we end up with 100 liters. So this is how much we would need to start out with in order to make this solution. The rest of what we use to get to the 500, we would add 400 liters, that's a lot. We would add 400 liters of water to make this concentration of 0.4 molar. Okay? Our next and final for this type of calculations for our quantitative concentrations is molality. Now this is different, you see, just by one letter than molarity, and it is represented instead of with a big M, it is a little lowercase m, okay? And molality is equal to the moles of solute divided by kilograms, okay? So the mass of the solvent. Note that this one is special because it's the only one that is talking about solvent instead of solution, okay? So in this case, in this example, and most of the time, the solvent is going to be water. So you can see our molality, our little m, is equal to our moles of solute divided by kilograms of solvent. So it's a comparison of mass. It's a different type of concentration that we're looking at. So our question is, calculate the molality of a solution containing 50.0 grams of sodium chloride dissolved in 3.00 kilograms of water. Now you can see right here that again we converted our 50 grams of sodium chloride into moles of sodium chloride. And so our molality, or our little m, is going to be equal to our moles of solute, which is 0.856 moles, divided by our kilograms of solvent. Now, thankfully, we were told what our solvent is, and it was already in kilograms. So moles per kilogram equals a little m, basically. And this is equal to 0.285 little m. Just like this was referred to as molar, this is referred to as molal, okay? And it is our molality. Sometimes you are going to see this not necessarily as kilograms of water, but you might see it as moles, and then you do have to make sure you convert it to mass before you plug it into our new equation. Did I forget anything? Think so far? We're good? Okay, so this would be our answer for this. And it's just another way to describe what's going on in a solution. Now, one of the reasons that we need to understand the previous concepts and be able to do all of these calculations is to understand colligative properties, which are basically properties that depend only on the number of particles dissolved in basically usually in water, and that's what we do in class, okay, in water. So our colligative properties are going to be our freezing point and our boiling point. We are going to learn right now how dissolving something in water actually changes the freezing point or the boiling point, okay? So first, before we actually do that, and we use this formula right here to do that, we have to solve for I. Now, I might seem like a very random or a number that, what is it called in math? A complex number or something, but it's very simple and basic and easy to figure out. For all non-electrolytes that basically are things that do not dissolve in water, so Ms. Frankovic talked about them in the last lecture a little bit, but they're basically molecular solutes. So anything that won't dissolve in water, I is always equal to 1 because it's not going to break down into anything. So this whole thing is just going to be 1 in water. But for ions or formula units, we know that those are going to dissolve in water, okay? So for things that are going to dissolve in water, like our salts, according to our solubility rules, figuring out I is a little bit different. You basically figure out how many things it breaks down into. So if I have 1 ion of sodium and 1 ion of chloride, this is going to be equal to 2. I equals 2. But for calcium, I have calcium chloride, I have 1 ion of calcium, 2 of chloride, so this is equal to 3. So my different types of colligative properties that we are going to be talking about are vapor pressure lowering, which I'll explain in class, freezing point depression, and boiling point elevation. Okay, so I'm going to start with boiling point elevation and use that as my example. So boiling point elevation just basically tells me that the boiling point of my solution with something dissolved in my water is going to be greater than 100 degrees Celsius. It is always going to cause the boiling point to increase. This is why you add salt to water when you boil and make pasta. Okay, so our example to calculate that actual change, delta, of our temperature, our boiling point, is going to be equal to K sub B, which is our constant that we're going to use right here, 0.52 degrees Celsius per mole. This is for molality, so this is why it's a little m and why we already talked about that. And so we use that equation. So if you can calculate the boiling point of 50 degrees or 50 grams of calcium chloride dissolved in 1.00 kilograms of water, basically all that you have to do is you find the molality and you find the number of moles of you already found the number of moles of our calcium chloride to find the molality, and then you plug it into this formula. So I go 0.52 degrees Celsius per mole, and then I multiply that by M, which is equal to my molality. These cancel out, times I, which for calcium chloride is 1, 2, 3, and I get the change in boiling point to be 0.704 degrees Celsius, We will talk about what that actually does to your boiling point in class.